I'll begin with a word of prayer. Dearly Father, we thank you for this morning. Again, Lord, we thank you. Thank you for your grace and mercy to us each and every day, Lord. We thank you that you love us even when we don't love you. We thank you. You came to earth and died for our sins, and let's accept you in our heart. You give us forgiveness, and we get your righteousness even though we don't deserve it, Lord. We thank you for that. I just pray you be with us this morning. Help us to understand a little bit more about differential equations. And in your name I pray, Lord Jesus. Amen. So I wanted to just remind you guys something, which should go without saying, but here I'm saying it, which is that I have notes posted that may or, well, I think they'll be helpful to you. And so, like, I wrote this, I wrote this in Microsoft Word, which is why I can no longer edit it. If you find an error in here, that's lovely, but I have no way of editing these, because one time I hit the wrong save button, and it forever saved them as an uneditable thing. So if there's some error in some equation here, I can't fix it. It's impossible. Sad. Which is why I no longer use Microsoft Word. Anyway, if you look through here, I have some just kind of leisurely discussions about what's a solution, what's a differential equation, and then example after example after example after example after example after example after example after, you get the idea. So there's like tons of examples in here for you to look at if you don't care for what I do today, yesterday, and tomorrow. Okay, so what I'm trying to tell you is if you need more examples and more advice about how to do the differential equations we're doing in here, it's in here, all right?
And that's on what book?
Good question. Where do you find this? So if we go to, I don't think it's on Blackboard. So if you go to the course website, under course notes, here's that's that chapter 9 thing we looked at, was right there, numerical integration techniques. And so it's actually chapter 16. Yeah. I mean, honestly, folks, you could teach this particular topic anytime after we do the integration theory. This semester I'm following Salas and Hilly, so I teach it right after the integration theory. But if you look at other calculus books, you might find it put other places, and that's why it's later in my course notes, because we were using a different book when I wrote these notes. But you know what? The math is the same. So. All right, so let me remind you, just briefly, integrating factor technique. What's it do? So basically, if we're given dy dx plus py is equal to q, then we can solve this by a series of steps. So step number 1, we set h equal to the exponential of the integral of p dx. Step number 2, we multiply, let me give this thing a name, star. Multiply star by h. So that gives us h dy dx plus ph y equals to hq. Step number 3, we check on reverse product rule. So if we calculated h correctly, what we'll be able to see is that star star is in fact ddx of hy. So that's equal to hq. Step 4 is we integrate both sides. Integrate star star star. To obtain hy is equal to the integral of hq dx. And step 5, solve for y. And this gives us what's called an explicit solution to the given differential equation, linear differential equation, which was, so there you go. There's your explicit general solution. Explicit general solution to star. This is the integrating factor technique. All right. Let me work an example. So what we're talking about today, guys, is I'm just going to review another example of the integrating factor technique to start with. All right. Once that's settled, I'm going to talk to you about the method of separation of variables. When I teach differential equations, I usually teach separation of variables first. I'm doing separation of variables second here just because I'm following Salas and Hilly. It's really nothing more than that. They are different techniques, but they're not mutually exclusive. They have overlap. Some problems can be solved either method. All right. So here we go. Suppose we wanted to solve dy dx is equal to, say, some constant k times y. All right, so how do I put this? First of all, I gotta repackage it, right? This is what? This is dy dx minus k times y is equal to 0. Now I've done what? I put it in standard form, right? This is a first order ODE. It's in standard form. The integrating factor technique will take care of it. Let's see how it does it. So what's my p? Right, p is equal to minus k. It's just a constant. So that's what? The integrating factor, h, is equal to the exponential of the integral of minus k dx. Well, that integral is easy, right? That's just what? E to the minus kx. We are now at step 1. Step 2. I multiply the differential equation by the integrating factor. So I have e to the minus kx dy dx minus k e to the minus kx y is equal to 0, because 0 times e to the minus kx is still 0. By the way, I have no expectation that you number your work 1, 2, 3, 4, 5. That is merely for your convenience following along. This is not part of what I expect you to know, okay? Like, it's not your job to multiply, to memorize that this is the series of steps we go through, and you must number them. I mean, I do expect you to go through this series of steps, but it doesn't have to be numbered. I want you to understand. So maybe I should be less organized, because right now I'm kind of giving you a formulaic way to solve these problems. Sorry about that. What's that? All I did, multiply that by h. Multiply the given differential equation by the integrating factor. That's the thing that's so interesting about this, is that multiplying the differential equation by the integrating factor changes it so that you can look at it and go, wait a second, that's exactly d dx of times y. That was step 3. Now step, it's so hot here in the morning. Whew. Oh, and at this point, I mean, usually I say you have to integrate both sides. I mean, we could still integrate both sides here, right? Fine, I'll do that. But I mean, another way to look at what I'm about to do is just, hey, we've just seen that this quantity's derivative is 0, so it's a constant, right? So from a theorem in Calculus 1, it immediately follows that what's in the parentheses has to be constant, right? But, you know, if you want to, you can look at it as integrating both sides. We get e to the minus kx. Y is equal to the integral of 0 dx, which is actually equal to c. Right? Any constant differentiates to 0. And then step 5, what we got? You guys follow? No? I multiply both sides of this equation by e to the kx. Yeah, that is the general solution. This is, yeah, well, this is a general, I mean, I would say this. I'm not sure your book has this language, but this is language I use. This is the explicit general solution. If I was to set this equal to that, that would give me a general solution, which was implicit. This is an implicit general solution. I'm not sure I mean, but well, yeah, I mean, that's not a bad language to know about, especially for the next topic. But an application of this example, I mean, this is an important example, right? How about population growth? dp dt is equal to kp has solution what? P of t is equal to some constant c times e to the kt, right? But if p of 0 is equal to p naught, then c is equal to p naught. Therefore, you can even write the formula like this, right? Sometimes it's desirable to write the solution in terms of an initial condition. So there's the solution written in terms of an arbitrary initial condition, the initial population. Yeah. Yeah, like that. Unless it's just impossible. I mean, there are problems where you simply cannot find the explicit general solution. We'll see one of those today. But generally speaking, it's desirable to find the explicit general solution if you can. All right. Can you guys think of any other applications? What's the other thing I told you guys last time? Yeah, Newton's law, but that was a different differential equation. The other one was dn dt equals like minus rn, yeah. So this has solution n of t equals to n naught e to the minus rt, where I'm using my experience with number 1 to just label the constant as what it is. It's the initial number before the radioactive decay happens. So what's the difference? If you have if k is positive, right? As time goes to infinity, what's the population do? Assuming the initial population is non-zero, it just keeps growing and growing and growing at a faster and faster and faster rate, infinite population, right? That's not realistic, right? Usually. On the other hand, what happens to the number of particles? Well, it goes to 0 for radioactive decay. You can also think about, like, what's the half-life? How would you find half-life? This isn't really calculus, this is more algebra, but let's talk about it for a second. Half-life, we would just look for, say, when n of t1/2 would be what? N naught over 2. So you just set that equal to what? N naught e to the minus r t1/2. And you can solve this, right? We get 1/2 is e to the minus r t1/2, right? Take the natural log of both sides. Put the minus over here, we get natural log of 2 equals r times the half-life. But that means that the half-life is the natural log of 2 divided by r, right? In fact, we can rewrite this solution in terms of half-life. So, I mean, that's the half-life, right? But if you look at this and stop and smell the roses here for a second, you see we also have a way, we could solve this for r, right? R is what? It's natural log of 2 divided by the half-life, right? So that's the relation between the growth rate and the half-life. What that means then is, of course, I can go back to the general solution, right? And I can rewrite it in terms of half-life if I'm so inclined. N of t is equal to n naught e to the, and what was r actually? What the lesson we just learned? R is what? It's minus r, right? So r is the natural log of 2 divided by the half-life. I'm regretting my symbol for half-life at this point. Oh well, it's too late. Times t. Can we simplify this? I mean, I can get rid of the minus by doing what? This is really n naught divided by, yeah, I'm going to write it as, bless you, t times the natural log of 2, right, divided by the half-life, right? I'm not sure that's helpful. Let me erase that. That's not a useful step. Let me try this again. Let's see here. So let me rewrite this as n naught e to the natural log of 2 to the what? To the, so if I bring the minus inside, well, fine. I'll just bring, so that's minus t divided by t1/2. See, I can use the power, sorry, I'm going to write this up here. This is the same as this, right? Agree? These are interchangeable. Sorry, I'm taking a break from calculus at the moment just to do some stuff with, I mean, it's basically pre-calculus calculation, right? But I think it's good for us all to see it again because there's a subset of you who aren't really quite comfortable with what I'm doing right now, and it would be good for you to try to understand what I'm doing. Let's see here. So this is minus t over t1/2, right? Natural log of 2. Do you agree? So the point is, I can use the property of the natural log, which says that that's 2 to the whatever's multiplying out here, right? If this is the power p, yeah. So that's why I get this natural log of 2 to that p. But of course, the natural log and exponential now are composed so they cancel out, right? They're inverse functions. And you're just left with n naught times 2 to the minus t divided by what? Good. Can we write that a different way? Is that right? I'm not sure about that step, actually. Yeah, I don't think that's right either. What we can do, though, is what? Yeah, I wanted, yeah, right, exactly. I wanted to make it like 1/2 to a power, right? 1/2 to the t divided by t1/2. There we go. Now I think that may be a formula you saw in middle school or something, depending on your science curriculum. So what you have then is when you set the time equal to the half-life, what happens? That factor becomes, set t equal to t1/2, what happens? What happens when you get to twice the half-life? You get 1/2 squared, right? 3 times the half-life, 1/2 cubed, right? So you get this halving and quartering and so forth and so on. So, all right, well, anyway, that's that. Sorry, I somehow have digressed into pre-calculus. My apologies. Now, you guys mentioned another application, I don't know if I called it the logistic equation. Did I call it the logistic equation last time? I don't remember if I did or not. I talked about a problem with carrying capacity. Right, so the technical name for that is the logistic equation. I think I neglected to actually say those words yesterday. I was reading your book this morning. I'm like, wait a minute, I forgot to call this the logistic equation. I wasn't doing my proper name calling yesterday. Sorry about that. So now I've named names. Let us go on to the other technique. Separation of variables. Let's see here. If I can, I'll try to present it as your book does. So what he does is he says, consider oh man, I can't. Do you have the book? There's a how he sets this up. It's okay. I'll steal Aaron's. I'm sorry, Thomas's. I keep thinking you're Aaron, which is just absurd. Oh, you're fine. You're fine. I got it. Yeah, we're 9.2. So he starts with, I need the setup, otherwise I'll waste your time. So he begins with a pair of functions, p and q, which have continuous derivatives. So he says, consider p and q with, section 9.2. Separation of variables. So he says, begin with a pair of functions p and q, which have continuous derivatives. So he says p prime is equal to little p, and q prime is equal to little q. All right. And he says he wants to form the equation p of x plus q of y is equal to c. Notice that in this equation, the x's and y's are not intermingled. They are separated. All right. Trying to behave and follow the book. This is not my usual starting point, so it's taking me a little thinking here to kind of follow along. All right, great. What are some examples of something like this? How about this? Just to make this a little bit less esoteric. Can you think of any things you know of that follow this pattern? Yeah, a circle's a great example. That's just the perfect example. So x squared plus y squared equals to r squared, a circle. Or how about one of these guys? -1. Ooh, this one. That one, we don't really need calculus to analyze that. What's that second one? X squared plus y squared equals to -1. All pairs of real numbers x comma y that satisfy x squared plus y squared equals to -1. It's the empty set. There is no such real number. So this equation has no solution set. I mean, the solution set is the empty set. Here, this is more interesting. This is a circle. This minus over here is important. Circle. This is a hyperbola, right? in fact, the list of things you can construct in this way are pretty much endless, right? It's very freeing. These don't have to be graphs, right? They don't have to pass the vertical line test. It's just a more or less arbitrary equation. Not quite, though, because we are assuming that you can separate the variables in this sense here, right? Okay, so then he's like, well, he was assuming that, oh, I think I've got it backwards. He says, P prime equals to, no, P prime equals to P. So his next move, he's like, so if you differentiate this, now, once he says differentiate, a little bit, he says, suppose y is equal to y of x. In other words, suppose that y can be solved to be a suppose basically we can solve, in principle at least, solve, let me call this thing star, solve star for y. Now that may not actually be possible, but there's something called the implicit function theorem, all right, which says that at least locally you can find y as a function of x, all right? Okay, so given that, what we really have for star is this. We've got, so if we differentiate implicitly then, we get what? We get p prime of x is equal, plus what? Plus q prime of y of x times dy dx is equal to 0. All right, but then in terms of the in terms of his little p and little q, he's like, it looks like this: p plus q dy dx equals to 0. Although I guess I should say it's really q of y of x. So that's kind of important. The dependence actually matters here. So we have p of x, q of y of x times dy dx equals to 0. And then what does he do? Well, this you can solve, right? I can actually solve this. I don't know if I can solve it or not, but I can certainly integrate this equation and get another equation. What does integrating that equation give you? Integrate with respect to x, right? So we have integral of dx I mean, I'm doing indefinite integrals. I'll just add the constant to the other side without loss of generality, right? Now, okay. Can you do anything? Can you do anything here to this? What is this really? Right. So if I make a u equals to y of x substitution, right? Then this is really, say, q of u du. But instead of saying u, we just say y, and think of y as an independent variable rather than a function of x. So if you'll allow me that notational cheat, which everybody makes, and you'll want to make too, this is just the integral of p dx plus the integral of q dy equals to a constant. And here, q is function of y. All right. Trying to follow the book and be a good citizen of mathematical world here. This is a pretty legitimate argument for why that's true, right? Let me show you some symbol pushing nonsense, which says the same thing. All right, time for symbol pushing nonsense. Here we go. We've got, what do we got? We got P plus Q dy dx equals to 0, right? Where Q is a function of y and P is a function of x, okay? Well, that's a cheat already. So what you do is just say, oh, okay, well, Q dy is equal to minus P dx. So what I'm writing in the green is the so-called method of differentials. It's formal calculation using differentials as if they're actual little real numbers that you can push around and treat like fractions. And well, what this formal derivation shows you is, in fact, that's true, right? Because what our outcome here is integrate both sides. And what do you got? You've got integral of Q dy is equal to minus the integral of P dx. Of course, you could rewrite this as like, integral P dx plus the integral of Q dy is equal to some constant. I mean, these are both indefinite integrals. You got to add a constant somewhere. So you see what I wrote in green is equivalent to what I've derived in a more stodgy way, mathematically correct. Although, honestly, folks, this is also has a giant gaping hole in it logically, because I supposed y is equal to y of x, right? And we haven't proved that. We won't prove that until advanced calculus. That's where we prove the implicit function theorem. So, and most of you won't take that course, so you'll forever be ignorant. Oh, I'm sorry. It's okay, though. We can work with partial knowledge. And we can work with partial knowledge, right? And assuming y is a function of x is not a bad thing. All right, let me work an example. You'll feel better after that. Suppose we look at this example. We just looked at it a minute ago. Let's look at it again. Dy dx is equal to ky. If you look at this, what I'm really saying is to take everything with y and put it to one side, and take everything with x and put it to the other side. All right? If you can do that, you can actually work these steps backwards, and you can rewrite it as a separable equation. Say again? Mm-hmm. Right. But be wary of my steps. I have integrated, all right? The left side I integrated with respect to y. The right side I've integrated with respect to x. But corresponding terms. There's something sneaky going on there. Which is why your book won't do it, because it's not rigorous mathematics. I'll show you more of how this works in just a second, okay? Let me remind myself. I should work this example if we have MA equals to, say, minus G. Then we can do something. V. All right. Okay, so here we separate variables, so we get dy. Come on. Dy divided by y is equal to k dx. All right? So just... Oh, by the way, make sure that it's not showing the tan above and below. Is it? Because we want to be, we don't really care about the wall above or below. We want to be just on the board. So, and I almost never write anything down here, so it's safe to, I don't typically write anything below kind of here. So it's usually safe to. All right. Sorry, it's especially true of the green that you might have to zoom in to see it sometimes. But all right, I digress. We separated the variables in terms of the differential notation, right? dy over y is equal to k dx, like that. And then what? Integrate both sides, right? So this gives me the natural log of the absolute value of y is equal to kx plus a constant. And then what? Now I can solve for, I want to find, that's an implicit general solution, getting back to our earlier discussion. Like this right here, if I was just looking for an implicit general solution, done, game over, there it is.
Okay.
But if I want more than that. I want the explicit solution. So I have to solve for y. Take the exponential of both sides, what do we get? We get the absolute value of y is equal to e to the kx plus c, right? Properties of exponential tell me that's e to the kx times e to the c, right? But then what? So this is y is equal to plus or minus e to the c times e to the kx. I'm going to put a tilde on these c's to suit my purposes, if you don't mind. There you go. Okay, so what you can do then is say, okay, I'm just going to call this whole thing in the front c. So that's c e to the kx. And there you go. We're back. After all, it's just an arbitrary constant. What does it matter whether you label it plus or minus the exponential of some other constant or just call it c? If I just say where c and c is a real number, what did I just add by saying that without restriction? What is in fact impossible? If your constant has a form plus or minus the exponential to some other constant, what does that mean? That means it's either positive with the plus or it's strictly negative with the minus, but certainly e to the plus or minus e to the c could never be what? Could never be 0, right? If I just write c e to the x, I've included the 0 solution, right? We know the 0 solution's in there because we worked it before with a different method over here, right? Is there any restriction that c be non-zero in this argument? Certainly not, right? C equal to 0 is a legitimate solution. Let me go back to the original equation, the derivative of the 0 function. What is it? Derivative of any constant function, 0, right? Plug it into the other side, k times 0, 0. Yes, the 0 solution is a solution. So it should be there. Why isn't it there? Why don't we have intellectual property rights to it from separation of variables? Like here. Why is y equal to 0 missing? I'm not really asking you that hard of a question. That is true, but that's not the reason. I mean, that is one reason. What I'm asking is in terms of our calculation, in terms of the steps we made, why did we lose y equals to 0 as a possible solution? You know what? You want to say it? Go for it. No. Good try, but no. How about up here? This step from here to here. What is this doing? Yes, sir.
Divided by y, so
We have a winner, right? Yeah, right there. Divided by y. Once you do that, you're not going to find y equal to 0 on purpose, right? If you don't pay attention, you might think you got it by writing that, but you added it, if you think about it. So that is one of the dangers of separation of variables. As we divide by one variable, we can lose, if that variable 0 is a solution, we'll lose that possibly in the general solution set. So that's the sort of the fine print here. But anyway, there it is. All right, I'm going to erase this stuff that I did from the book because it doesn't really matter to us that much, and I want to show you a bunch of examples. Let's do that. You notice I really wasn't thinking through this stuff when I did it? You know? It's almost too easy, isn't it, that it works this way? All right, so what we get is we've got y dy is equal to minus x dx. So when you integrate differentials of different variables like this, what this is, all right, is what I just erased. It's actually a clever application of the U-substitution. Right? If you make a U-substitution, you have to change the bounds accordingly. Right? So if I was to do this, I could integrate this, say from from y naught to well, let's say y, and I can integrate this from x naught to say x. Now, if I do that, then I'm thinking of x and y as fixed but arbitrary variables, right? And technically speaking, I really shouldn't use the integration variable and the fixed but arbitrary variables. I'm looking for x and y in the same way. So a way to, not be mathematically heretical is just to put some bars here, and then you're good to go. So this integrates to what? 1/2 y bar squared, right? I have to evaluate that from y naught to y, and that's equal to minus 1/2 x bar squared. Evaluate that from x naught to x. The introduction of the bar is just as to not confuse between the integration variable and the fixed but arbitrary constants the constant fixed but arbitrary variables x and y I'm trying to find. Anyway, what does this give us? This gives us 1/2 y squared minus y naught squared minus 1/2 x squared minus x naught squared. And you can solve this for x squared plus y squared equals to x naught squared plus y naught squared. I don't usually solve these this way. But if I do, it builds a point of the solution already into it, right? Like, what is this? It's a circle, right? And it's a circle that has point x naught y naught onto it, right? So integrating the x and the y over corresponding values like this will automatically build a point in the solution into it. If you do it for an arbitrary point like x naught y naught, it's pretty cool, right? I don't know. I think it's neat, but you can disagree. Let me do this example in my usual freewheeling, not so careful way. I mean, not caring about x naught and y naught. So I get minus y dy equals minus x dx. Integrate both sides. What do you get? 1/2 y squared equals to minus 1/2 x squared plus a constant. There you go. X squared plus y squared is equal to 2 times c. There's the implicit general solution. Obviously, that's not as useful a solution as the one I have to the left, right? Because the one on the left automatically builds like one point on the solution into it. Now, here, before I find an explicit solution, what do I need to know? Right. So like up here, we'd have y is equal to the square root of 2c minus x squared. But down here, well, this is also filled in. we have y is equal to minus the square root of 2c minus x squared, right? This is an example of what I was talking about, this implicit function theorem. It says you can solve for y as a function of x, right? Given an equation that involves x and y, you can solve for y as a function of x given certain conditions. All right? Where on the circle can you not solve for y as a function of x? There's 2 points. Right here, you can't solve for y as a function of x like that. Because anytime you try to solve for these pieces right here at the, on the x-axis, those points you're going to fail the vertical line test, right? You'll definitely cut through this solution 2 points if you think about it. It's no accident that that's exactly where this differential equation is not defined either. See that? That's where y equals to 0. Oops. So these things are more explained in their entirety in advanced calculus, but anyway. Any questions? I just go on and solve some more, if you don't mind. You can stop me and ask me questions as we go on here at any time. So this is a famous problem in physics, right? ma is equal to minus g, where v is dy dx. I'm thinking y to be the positive direction. And so we can look at this as m dv dt equals to minus g, right? So let's see here. I can look at this, of course, as dv equals minus g over, what? Something feels wrong. Oh, what am I missing? Don't tell my physics students. Yeah, it's mg, right? Otherwise, this was dimensionally inconsistent, right? I can't have a force is equal to an acceleration. That's nonsense. Now, the interesting thing, of course, is the m goes away. So apparently Aristotle was wrong. The ways things move, it doesn't depend on their mass, right? There's not different laws of physics for heavy things and for for not so heavy things. In fact, we all the different things accelerate the same way. In other words, you divide by m, you get the acceleration is minus g, right? Okay. So that gives me dv dt is equal to minus g, right? So I can do this. I have dv is equal to minus gd. I separated the variables. And then I can integrate dv from, say, v0 to v1. And I could integrate the other one, gdt, from, say, t0 to t1. This is another way of getting around this is yet another notational scheme. So we have v1 minus v0 is equal to minus g times t1 minus t0. And this gives us v1 is equal to v0 minus g times t minus t1 minus t0. Or if you just set t1 equals to t, you get v of t is equal to v0 minus g times t minus t0. So here's an entirely new example for you. You never saw this before, right? We couldn't ever do this in calculus before this point. No, of course we could, right? But separation of variables gives us yet another way to look at problems we could do before just with integration, right? It gives us a fresh look at U-substitution. It's really just a really good notation for U-substitution is what it is. Let me pick up on that example again and work in a rather different way. A equals to minus g, right? So we have dv dt, but here's a trick. We could write that as dy dt times dv dy by the chain rule. Thinking of y, so here I'm thinking of v as a function of y. So this is just a sneaky identity. We can rewrite the acceleration, right, as this, but what is this? What's dy dt? The change in position with respect to change in time, the instantaneous rate of change is the velocity. So this is v dv dy. All right? So we have v dv dy. Sorry, I like to say that for some reason. Is equal to minus g. And now you can separate variables. So what we got is we got v dv is equal to minus g dy. Separate variables. At the level of the derivatives, at the level of differentials, we separated the variables. And then you integrate both sides. I say v naught to vf and y naught to yf. That's the U-Substitution Theorem in this notation is all that is. But I have to integrate over corresponding ranges of velocity and position, right? Like the v naught is the velocity when y is equal to y naught. Vf is the velocity when the y is equal to yf. Does that make sense? I think it's intuitively very natural, and the mathematics is just, again, the U-Substitution Theorem. So what you got is you got 1/2 vf squared minus v naught squared is equal to minus g times yf minus y naught. And there you have it. Vf squared is equal to v naught squared minus twice gravity yf minus y naught. You may recognize this from your physics course, right? This is the timeless equation. Well, that's what I call it anyway. I think you can see why I call it that, right? A couple of your homework problems have something kind of like this, but it's a little bit different. Let me show you the difference. Let me work something sort of like one of your homework problems, but a little bit more out there. So suppose that you've got a friction force that's something like minus beta times the cube of the velocity. So frictional forces are more complicated. Like the reality of frictional forces in aerodynamics is over different ranges of velocity, you have different power dependence. So the actual friction force for a specific object is probably something more like v to the some function of v up here. It's really complicated, generally speaking. But as long as we're like close to some specific speed, this is actually a somewhat reasonable friction force for certain objects. So then the question is, what's the velocity as a function of position? So, I could ask you a couple different questions, but I'm going to do that. Find velocity as function of x. So here I'm going to assume that v is equal to dx dt, okay? So I've got ma is equal to minus beta v cubed. That's Newton's second law. So I'm assuming that the net force is the force of friction. Okay. So this gives me acceleration is minus beta over m v cubed, right? But I use the trick I just showed you guys in the last example. I rewrite acceleration as what? V dv dy, dx rather. If x is the coordinate here, not y, then I have v dv dx by this same trick, right? So then what do I do? Separate variables, right? So everything with v goes to one side, everything without v goes to the other side. Let's see here. So I'll put, this gives me dv over v squared, right, equals to what? So I've separated variables at the level of differentials. Now I do what we've been doing, integrate both sides. And so I get like minus 1 over v is equal to minus beta x over m, and then plus a constant, right? Which gives us what? Flip it, right? V is equal to 1 over beta x over m minus c. There you go. There's the velocity as a function of position. If you have a cubic dependence of the friction force on velocity. I think in your homework there's one that's like a square dependence or maybe a linear dependence. Yeah.
Can you explain again what you did with the arrow from A?
Yeah, sure. So what's between here and here is the following. We've got A is equal to dv dt, right? But if I rewrite that in terms of x, this is dx dt. Now this assumes one-dimensional motion. I certainly couldn't do this for like something more complicated, but for one-dimensional motion, I can make this trick. I can reparameterize the velocity instead of a function of time as a function of position. But that's what this is, v dv dx. So it's just a sneaky trick to rewrite rewrite acceleration in terms of velocity and the derivative with respect to position. Now, what other thing might you ask about this example? Here's a different take on this example. Again, let's look at the force of friction minus beta v cubed, and then let's find the velocity as function of time. That's a different differential equation, right? So now Newton's law, well, it's still Newton's second law, ma, is equal to the net force, which we're assuming is just the friction force, minus beta v cubed. But this time, no v dv dx trick. It's just straight. We've got m dv dt, right, is equal to minus beta v cubed. And then what do we get? So you now separate variables, right? Separate variables. What does that give us? So you guys tell me what's on the other side. Minus beta over m what? dt, yeah. The v cubed's on the other side now. That's the idea. And now you can integrate both sides, right? And we get, what do we get? Minus 1 over 2 v squared, I believe. Yeah, equals to minus beta t over m plus some constant. So I can solve this. This gives me v squared equals to fine, let me think a little bit harder about this. All right, so I'll just flip both sides to start with. That gives me, and multiply by minus squared. I get 2v squared is equal to, 1 over c, or 1 over beta t over m minus c. So v is equal to plus or minus 1 over the square root of 2 beta t over m minus 2c. So there's the velocity as a function of time.